personal reading. But again, that is basically the way it works. If you can teach yourself some things, then for us, we see how you're learning that, and then we welcome. And always feel free to ask me. You can always reach out if you have any question and ask.
I personally will.
Great. I think one day I'll take you into journalism. You might be very good at that as well.
Who, me or all of us?
I think Ian doesn't ask so many questions, but you're doing well.
Thank you.
I've shared uh, a website to act as an inspiration. So basically, and that's why I need someone to describe for us what the name Deep Minds mean, the inspiration behind, such that we can write a description, define our identity. But then the rest is more of the team which we have now and what we do so far. But so we just keep adding as we move forward. Yeah, and it you came up with Deep Minds. Ah, okay. Mm. So we might need to change it slightly. We might need to change it slightly such that we are not getting confused. Yeah. That is now up to you to suggest for us and give us a description. Then we can react to whatever you will have suggested. Right.
Thank you. It's not so long presentation. It's just covering confusion matrix today, as requested by Mr. Chimera. So, starting with what is a confusion matrix? Keyword here is the matrix. We all know okay, assuming we know what a matrix is, sort of a summarized table, we usually with numbers, but this is going to be with a binary set of data. So a confusion matrix is a fundamental tool in machine learning, particularly for evaluating the performance of characteristic classification algorithms. It's a table summarization of predictions made by a classification model against its actual values. So in my previous discussion, there was a small table on predicted guilty and not guilty, and it showed different columns with who was actually guilty and was predicted guilty, and who was not but predicted guilty. Things like that. That's a type of thing I'm going to look at. So in a simple way, it's a layout of how many predicted categories or classes were correctly predicted and how many were not. So if we're building a model, our our idea here, what we're trying to do is to make the model make better predictions. An example, if we wanted our model to distinguish between different animals from various pictures, like cats, dogs, birds, giraffes, they all have different features. So using previous pictures from previous features that it has used before, we want to see how good it is at predicting new pictures, because some cats look like dogs, okay, not look like, but have similar features, and we want to see if it gets confused by these features or it gives you an accurate prediction. So we tabulate that in some sense. So first we need to understand true positives and true negatives, false positives and false negatives. So we're going to have two classes, class A and class B. One is the positive class, the other is the negative class. Positive class, a true positive is that in the positive class, a correct prediction was made. A true negative, in the negative class, a true prediction was made. Then the false positive, in the positive class, a false prediction was made. So if it is in the previous example of guilty, not guilty, a true positive would be if our positive class is guilty and our negative class is not guilty, a true positive would be was predicted guilty and is actually guilty. A false positive would be predicted guilty, that means predicted in the positive class, but did not actually commit the crime, so it was a false prediction. True negative, not guilty. You are predicted not guilty and you actually did not do it. False negative, you are predicted not guilty but actually committed the crime. It sounds confusing at the start, but with time it gets easier to understand. So if A is a positive and B is a negative, then a correct prediction of class A is a true positive, and a correct prediction of B is a true negative. What is our goal? We want to get as many predictions as possible and aim at getting more truths. So if we're building a model, we're going to test it with if we're building a model that identifies animal types, we're going to test it with as many animal pictures as we can get, so that we get as many predictions as there are, and gauge if the accuracy levels are high or low in order to improve or leave it as it is. And we want to get more truths in order to gauge our accuracy levels. Now, how to organize the matrix. I gave an example. Consider you built a delivery app and gave it a functionality to detect defective items and non-defective items. So we're going to have two classes, class A and class B. That is a positive class and a negative class. So our goal here is to detect defective items so that we do not deliver them. So here, there's a line here with predicted defective is a positive class. So the item here, we gave it 1. 0 represents non-defective, 1 represents defective. So with our first item, we said it's defective. Second item, we said it's not defective. So every one you see is for defective, and every 0 is for a non-defective. But then the true defective items are in black. The first item was truly defective as we predicted it. That makes it that it is in the positive class and it is true, which makes it a true positive. The second item was non-defective and it was predicted as non-defective. So it is in the negative class and it is true. Now in the third item, we predicted it as defective, but the actual truth is that it is not defective. So this is in the positive class, but our prediction was false. Another example in case, we predicted the fourth item to be non-defective. The actual item was defective. So in the negative class, our prediction was false. I hope that makes sense. Then we can tabulate our results. With defective, I tried to label as so that you can understand. Defective, these are our predicted values, and non-defective, still predicted values. Then the defective, actual, and defective, non-actual. So from our previous table, I counted out how many true positives, like defective. How many predictions in the positive class did we make that were actually true? I come here, true positives, it was one true positive. So that's how I constructed, this is the matrix. And the values here, 1, 2, 1, 2, they're from the previous table. I'm creating a matrix from the information I have, from the predicted values and from the actual values the actual values tallying with the predicted ones to see how many truths I got. Then key matrix derived from a confusion matrix. What are we aiming to get? We're trying to find out how accurate the model is, the precision, and recall. So these are the formulas for calculating that. Accuracy will equal true positive plus true negative out of true positive plus false negative plus false positive plus true negative. I wrote down the formulas, and all of them are tallying to the example above. Applications of the confusion matrix. It's used in binary classification problems, like the ones we've been mentioning, a model having to identify two classes apart. Then evaluating the accuracy of diagnostic tests for diseases. It can help you identify who is sick and who is not sick. So you have class 1, a patient is diagnosed as sick, class 2, not sick. So you can use a confusion matrix to see how accurate your predictions are. Then assessing how well an email filter identifies spams. We have spam messages and emails that are not spam. So how well does your the algorithm that you're using, how well is it classifying emails to actually send to you that are not spam? And is it sending you some emails that are spam? Then determining the effectiveness of models in identifying fraudulent transactions, that is minimizing online fraud, analyzing the performance of models in classifying objects in images. I gave that quite a lot of times as I was explaining. Then understanding how accurately models predict customer attrition. That is in like finance with people having businesses, predicting whether the customers will come back or if they'll not, if they'll continue to support the business or not. Why is a confusion matrix called confusing? When I first heard the term confusion matrix, I thought it was because it was confusing, but as that is far from why it's called the confusion matrix. It's right here, it's not because it is confusing in the sense, but rather because it shows you how much your model confuses one class with another. So if we have two classes and want to see if our model can correctly identify each class, the confusion matrix helps us understand how many times it's going to confuse the two classes. So we are trying to measure out its flaws and minimize them. And the name comes from the fact that it helps you see where your classification model is confused, meaning which classes it is mixing up or misclassifying. There's advantages, provides detailed breakdown of correct and incorrect predictions for each class, helps identify the types of errors your model is making, the false positives versus false negatives, allows for the calculation of various performance metrics beyond simple accuracy, which is crucial for imbalanced datasets, offers insights into where the model needs improvement. Thank you. I've gone past my time. I apologize. But if you have questions, I'll take them.
Interesting. Mine is not a question.
Yes.
You really discussed it clearly. And it can, of course, go beyond binary classification to multi-classification. So you'll find very huge confusion matrices with so many variables. And when you find them, remember it's read diagonally.
Yeah.
And some of them, even the way when we use some tools, especially Python, the coloring can already show you which classes are predicted right and which one are predicted false. And so you could explore that. But I had one question, something to think about.
Yes.
Most of the times, the confusion matrix will show us uh, yes, true positives, true negatives, and the like, or false positives or false negatives. But don't you think we also have some classes that are in between? And now I'm borrowing the idea of quantum computing. What do you think?
Um, do I think sometimes what?
There are some, it could be a binary classification. Let's say dog, you're just identifying dogs and wolves.
Yeah.
But there is a possibility that something is 50-50.
Yeah.
How do you think we could classify that?
I would use a different algorithm.
Now, why? Okay, would you create another class?
Would I create another class? Not in the sense. It's a 50-50 percentage.
Probability, if you want to.
Yeah, probability, actually. That's assuming I know the actual value.
Yeah. The
If I know
value is,
that, sorry, you wanted to say something?
no, I'm saying the value is 50.
Yes, the value according to the model is 50. But I know that what I expect, what I want, if I'm training the model. So in the sense that I'm training the model. And I input a fox and a dog, is what you said.
Mm.
That is a bit confusing. But as a trainer, I know what I expect. And basing off the features the model uses to come up with a prediction, I could adjust that. Now, the issue will come in with me not being the designer and wanting actual output.
Yeah.
Me as the user, if I became the
So
user and the model had what should I call it, a glitch.
you are the designer, you are the engineer, and these
Yes.
are engineering problems. So I'm not actually asking for an answer. I just want you to think about it
Yes.
because it is possible. In the real world, definitely we would say model has a problem. But then,
Yeah.
what if it is a fact and want to take care of it? There are cases where this could be true. Something is just 50-50. Probability it exists. So that is something you can think about. And I don't know if Ian could explore the quantum computing side. How, so this is when you could now start saying, okay, could I use quantum computing to represent this neutral class? That's when that comes up. But just think about it. You don't have really to give an answer.
All right, I will. Thank you.
You're welcome.
Okay. Now I have to run off.
Okay.
Have a nice day.
Thank you, and you too.
Ian as well. Thank you.
Hmm. Okay, I'm pushing this problem to you. If you can next time, please share with us what you think or how you think it could be handled. You can discuss with Tracy, pick it from that perspective of binary, and then I have this. Uh, the term has gone. What's that property in quantum? Yes, something is in two positions. That's superposition. So think about it. How could it be represented? I mean, I know there are kits that you can use to represent superposition. But in reality, could you think of a real world example that someone could easily work with? And then using a confusion matrix. So you improve the confusion matrix to now add that variable. Then two, what do we do? Because it seems there is no one else to learn and probably ask some questions. Do you mind if we push your presentation to next weekend? Or you wanted to just record it and then next weekend you share something else? Okay, please go ahead. Oh, I think you're muted. I was wondering why I wasn't hearing. It's okay. You have muted yourself. Hmm. Thank you, Ian. This is interesting. I think one other thing you want to explore is how most of these gates are represented in linear algebra. Their core, it's easier to understand why they change from one state to another when you're using the linear algebra concept. I'm sure you've already seen some of them, but I also know sometimes it's a bit complex to transform, because at the end of the day, even if the qubits are in different states, they're always going to collapse to binary state for representation. And I think also I should remember to share some resources with you where you can actually do some practice to run some of these. Oh, the practical bit of it. Okay, but I think you can check out the IBM Quantum platform. I think you can just use it for free to simulate some experiments. Yeah, that's all from me. You're welcome. Thank you to Ian. Hmm. Hmm. So when Trace was talking about some of those concepts, they were not new anymore. Okay. Please feel free to share. If you have anything not share, put it on our group such that Ronald can also know what's going on. And uh, continue. I think I've already told Tracy what to do on that group. In like, I think I've already told Tracy what to do to try and understand the mathematics behind one of those machine learning algorithms. So kindly do the same for next week. I think I just asked for linear regression, and then any of those classification algorithm, machine learning algorithms, whether you choose an SVM or random forest or decision tree, any, except so long as it can do classification. We try to understand that little engineering behind. Yeah. So I wish you a wonderful weekend then. You're welcome.